One of the most interesting questions in science isn't about something we've discovered. It's about something we haven't found. And that question was asked by a physicist named Enrico Fermi back in 1950. He was sitting down having lunch with some colleagues, and they were talking about whether alien life existed out there in the universe. And then Fermi asked something wonderfully simple. Where is everybody? Now that seems like an odd thing to get worried about. But think about what he was really asking. If the universe is this enormous old thing, and it is, with billions and billions of stars, and many of those stars must have planets, and some of those planets must have life, and some of that life must be intelligent. Then where are they? Why haven't they visited us? Why haven't we seen their spaceships? Why haven't we detected their radio signals? This became known as the Fermi Paradox, and it's actually a profound question. Not because it's mysterious in a supernatural way, but because the answer involves some beautiful physics that I want to talk to you about today. You see, there's a very simple explanation for why we don't see alien visitors, even if they're out there. And the explanation is that interstellar travel, traveling between the stars, is incredibly, almost impossibly difficult. And the problem isn't that we haven't invented the right technology yet. The problem is the laws of physics themselves. Let me start with something basic. The next star over from us is called Proxima Centauri. It's the closest star to our sun besides the sun itself. And it's about 4¼ light years away. Now, what does that mean? Well, light is the fastest thing in the universe. Nothing can go faster than light. This isn't just something that's true right now with our current technology. It's a fundamental law of nature. Einstein figured this out, and it's been confirmed 1,000 times over. Light travels at about 300,000 kilometers per second. And even going at that speed, the speed of nothing can match. It takes light over 4 years to get from here to Proxima Centauri. Now, let me put that in perspective for you. The distance to Proxima Centauri is roughly 40 trillion kilometers. If you wanted to send a spaceship there, and you wanted to get there in, say, a human lifetime, let's be generous and say 50 years, you'd have to go at about 10% the speed of light. Just 10%. That doesn't sound too bad when you say it fast. But let me ask you a question. How much energy would that take? Well, we can calculate this. And the answer is, it would take more energy than humanity currently produces in an entire year, just to accelerate one spacecraft to 10% of light speed. Not to keep it going, just to speed it up initially. You understand, that's with our current understanding of physics and energy production. An advanced alien civilization would be able to do this more efficiently, sure, but they still wouldn't be able to do it easily. And here's the thing that most people don't think about. 10% of light speed is still incredibly slow when you're talking about traveling across the galaxy. The Milky Way, our galaxy, is about 100,000 light years across. That means at 10% of light speed, the trip would take 1,000,000 years. 1,000,000 years. For just one journey across the galaxy. Even if you're an advanced civilization with amazing technology, do you spend 1,000,000 years traveling? But wait, there's more. There's something else we have to consider, and this is where Einstein comes back in. When you start moving really fast, when you get close to the speed of light, something weird happens. Time itself starts to slow down for you. This isn't magic or anything. This is just how the universe works. It's called time dilation, and it's real. If you traveled at, say, 99% of the speed of light to some distant star, you might experience only a few years of travel. But here on Earth, centuries would pass. So from your perspective, you took a quick trip. But everyone you ever knew is now long dead. Their civilizations have changed, evolved, possibly even disappeared. You'd come back to a completely alien world. That's a pretty lonely voyage, isn't it? There's another problem I want to talk about, and it's one that really bothers engineers. It's called the tyranny of the rocket equation. You see, to go fast in space, you need fuel. Lots of fuel. And not just fuel to push the spacecraft. You need fuel to push the fuel. You need fuel to push the fuel that pushes the fuel. It's a cascade, and it gets out of hand very quickly. A scientist named Konstantin Tsiolkovsky worked this out, and what he discovered is that to reach really high velocities, the spacecraft has to be almost entirely made of fuel. The actual payload, the people, the equipment, the cargo, becomes a tiny, tiny fraction of the total mass. So if you wanted to send a spacecraft to Proxima Centauri in 50 years, carrying actual people, the fuel requirements would be so enormous that the spacecraft would have to be the size of, well, a mountain. Literally. And that's assuming you find fuel with incredibly high energy density. The best fuel we have is antimatter. Matter and antimatter annihilating each other in a burst of pure energy. But we can barely produce or contain antimatter. An advanced civilization might do this better, but it's still fundamentally difficult. Now, someone might say, well, why don't we just go faster? Let's build a spacecraft that goes at, I don't know, 50% the speed of light. Good question. Here's the answer. As you approach the speed of light, something happens according to relativity. Your mass increases, not your weight, your actual mass. And the more mass you have, the more energy you need to accelerate it further. By the time you get to really high speeds, you're hitting an asymptote. The closer you get to light speed, the more and more energy you need to push a little bit faster. In fact, to reach the speed of light itself would require infinite energy, which is impossible. You can never actually reach it. You can get close, but never quite there. So think about this. An advanced alien civilization has to deal with the same laws of physics that we do. The speed of light is the speed of light. Relativity is relativity. Einstein doesn't care how smart you are. These laws apply to everyone, everywhere in the universe. So no matter how advanced they are, they're still constrained by the same fundamental limitations. But wait, there's more problems. Let's say somehow you've solved the energy problem. Let's say you figured out how to build a spacecraft that can go at significant fractions of light speed. Now you have to navigate through space. And space isn't actually empty, you know. There are asteroids, there are comets, there's dust, there are particles. And if you're traveling at, let's say, 50% the speed of light, which is 150,000 kilometers per second, and you hit a pebble, just a little rock, what happens? The impact energy is enormous. It's equivalent to a nuclear explosion, a small nuclear bomb, just from hitting a pebble. So now you need advanced shielding. You need sophisticated detection systems to see hazards coming toward you. You need to plot courses that avoid all of this stuff. And you're doing this over journeys that take decades or centuries. That's incredibly difficult. And here's something else. Keeping biological creatures alive over those timescales is its own nightmare. You need food, water, oxygen, the right temperature, radiation shielding. The human body isn't designed for years of weightlessness. Bones get weaker, muscles atrophy, your immune system goes weird. You'd need life support systems that work perfectly for centuries. Any failure, and everyone dies. Some people have suggested cryogenic sleep, freezing people, putting them into hibernation, and waking them up when you arrive. Sounds great, right? Except we can't actually do this. We've tried with animals, and it's incredibly difficult. We don't even know if we could freeze humans without destroying their brains. And even if we could, what happens to all the biological systems over hundreds of years? The equipment breaks down. Life is fragile. So here's what an advanced civilization might do instead. Forget about sending biological creatures. Send robots. Send artificial intelligence. Those don't need food. They don't deteriorate over centuries. They can be incredibly robust. A robot could survive the radiation, the cold, the impacts. It could travel for 1,000 years and still function. That's much more practical for interstellar exploration. And actually, this might explain something important. You see, some scientists have proposed that if aliens are exploring the galaxy, they're probably doing it with self-replicating probes. Robotic spacecraft that can make copies of themselves, repair themselves, and spread throughout the galaxy. If this happened billions of years ago, and remember, many stars are much older than our sun, then the galaxy should be full of these old alien probes. They should be everywhere. Some of them might be nearby, but we don't see any. We don't see evidence of any old alien machinery. We don't detect any radio signals. We don't see any megastructures or evidence of massive energy use in other star systems. Nothing. And that's what the Fermi Paradox is really about. It's not just, why haven't they visited us? It's, why don't we see any evidence of their existence at all? Now, there's one more thing I want to talk about, and it's a bit more speculative, but it's interesting. Some physicists have suggested that maybe we could bypass the speed of light limitation using something called a wormhole. Einstein's equations actually allow for wormholes. They're solutions to the equations, mathematically valid. A wormhole would be like a tunnel through space-time that connects two distant regions of space, so you could travel between them without actually covering the distance. Sounds amazing, right? Except there's a problem. These wormholes would be unstable. They would collapse almost instantly unless you held them open with exotic matter, matter with negative energy density, also called exotic matter. And we have no idea if exotic matter even exists or if you could get enough of it to keep a wormhole open. It's theoretically allowed by the equations, but practically, we have no idea. It might be impossible. Similar ideas have been proposed about warp drives, using gravity to bend space in front of a spacecraft and straighten it behind, creating a bubble of space that moves faster than light. Again, mathematically allowed by general relativity. But the energy requirements are absurd. You'd need more energy than exists in the observable universe. And you'd need exotic matter. Again, we don't know if this is really possible. So here's the thing. Maybe there are clever tricks using physics that we don't understand yet. Maybe there's something about the universe that we're missing. But we have to work with what we know, and what we know is that it's incredibly difficult to travel between the stars. Incredibly difficult. Now, let me put this all together. The Fermi Paradox says, given that the universe is old and huge and full of stars and planets,